Hello everyone, in this video I will explain example 8.2, which is about determining the pumping power required for all flowing through a pipe. We will calculate the volume flow rate, determine the flow regime, find the pressure drop, and finally calculate the pumping. So given data is leg equal to 230, then have pipe diameter, then oil density rho 894 mu 233 kilo per meter second. Lastly, we have average velocity, which is 0.5. Value flow rate formula is V mass flow rate equal to V pi d2 over 4 into this formula. Then lastly we get 0.30779 meter cube per second. The formula for real number is Re rho Vd over mu. Then lastly we get Re equal to 53.7. Since Re is lower than 2300, this formula will include as laminar. So the third is we must find the friction flow. For laminar flow, the formula is F equal to 64 over Re. And lastly we get F equal to FLD rho V2 equal to over 2. Insert this formula. Lastly we get 156.9 kilopascal. How we get the kilopascal? We convert it. This one the data. We insert it. 0.0308 times 156.9. Then lastly we get 4.83 kilowatt. How we get the kilowatt? We must convert it into this. This is the formula. So the conclusion is pressure loss in pipe is 156.9 kilopascal. The power required is 4.83 kilowatt. So the conclusion is actually the pump power will be higher due to efficiency loss. So thank you. Hello everyone. In this example, we study about water flowing through a gradual pipe expansion. So the pipe expand from 6 cm diameter into 9 cm. The upstream condition is velocity equal to 7 meter per second and pressure equal to 150 kilopascal, 10 degree. So some energy will lost. As then our goal is to find downstream velocity, which we call it as V2. Then we must find the head loss, HL, and lastly we must find the downstream pressure, which we call it as P2. We must find the downstream velocity using continuity. Because the mass flow rate is constant, the formula is V2 equal to V1 area 1 over area 2. So area depends on the meter square. So we'll substitute the value equal to 7.062 over 0.192. So the result we get V2 equal to 3.11 meter per second. So the key point is velocity decrease when the pipe expand. We must find the head loss. So the formula for head loss is HL equal to KL V1 over 2G. So given loss coefficient is K1 equal to 0.1333. We insert the data into the formula. 0.333 meter. So the meaning is some energy will lost due to the turbulence as water spreads out. So the water spread out, the turbulence will drop. We must apply the energy equation to find P2. So the formula is P1 equal to P rho G alpha 1 equal to P1 equal to P2 rho G plus alpha 2 P2 to 2G plus HL. So as you can see, this is the formula. Okay, in this area, why we cut H pump and H turbulent, also Z1 and Z2, because this did not include into this into the data. So lastly we get alpha 1 equal to alpha 2, and the answer is 1.06. We substitute all the values into upstream pressure head, velocity head for V1 and V2, and lastly head loss HL into the formula, into this formula. So you can see we insert into this formula. Then the final answer we get P2 equal 168 kilopascal. So why the pressure increase? It's because when velocity drops, some velocity energy become pressure energy. In this case, pressure gain from velocity drop. Then pressure loss due to the turbulence. So the net result is pressure rise from 150 kilopascal to 168 kilopascal. So the final conclusion is downstream velocity equal to 3.11 meter per second, HL equal to 0.333 meter, L downstream pressure 180 kilopascal. In gradual expansion, velocity decrease, pressure increase, and a small energy loss occurs to turbulence. So that's all for me. Thank you for hearing.